So our speaker today is Scott Schmieding, and his title, as you can see there, is Symbolic Dynamics, Strong Shift Equivalence, and the Stable Algebra of Matrices. Please, Scott, go ahead.
Thank you. Thanks for the invitation. And yeah, I'm gonna maybe make a warning that the talk is gonna be kind of a survey in a way. So there'll probably be not very many. There won't be very much in the form of proofs, but I'm happy to elaborate, and I strongly encourage anyone to interrupt me and ask questions at any point. So let me start with the definition. And in general, throughout the talk, I'm going to be kind of working in the setting of a arbitrary ring or semi-ring. And I mean, for many places in the beginning, I guess you can think of R as being Z or Z plus, non-negative integers. So this is a definition due to Bob Williams called strong shift equivalence. And it's a relation on square matrices over your ring or semi-ring. And to start, you define two square matrices to be elementary strong shift equivalent if you can find R and S over the ring or semi-ring that satisfy this equation. So just a few comments. A and B both need to be square, but R and S need not be square. And in particular, A and B can be elementary strong shift equivalent, but need not be the same size. So one thing to note is that this is not an equivalence relation in general, because it fails to be transitive, or it can fail to be transitive. So you can take the transitive closure. You can generate an equivalence relation, and this is called strong shift equivalence. So to put this another way, two square matrices over a ring R, or R could be a semi-ring, are strong shift equivalent over this semi-ring if you have a chain of elementary strong shift equivalences between them. And it doesn't say anything about how long the chain can be, just that there's some chain of ESSERs is how I'll abbreviate elementary strong shift equivalences. And just as a toy example, you can check the matrix 2 and the matrix 1, 1, 1, 1 they're actually elementary strong shift equivalent over Z plus, the non-negative integers. So this is the strong shift equivalence is an equivalence relation. It's essentially an exercise. And it's interesting because it's a relation on matrices over ring or semi-ring, but it was sort of originally introduced by Williams, kind of motivated by some things in symbolic dynamics. So at the time, Williams was studying something called shifts of finite type. And there was a problem that had been lurking around, which essentially is called the classification problem. And before I pose this, let me tell you what a shift of finite type is. So you can start with a finite directed graph, and you can consider its set of edges. And then you define a set, which is the set of, essentially the set of bi-infinite walks through edges of this graph. So you can think of points in X gamma as being two-sided infinite strings, each of whose coordinate is an edge of this graph. And you have a so-called shift map, which just takes a two-sided bi-infinite string and shift the coordinates as I wrote. Sort of pick it up and shift it to the left. And if you equip this thing with the product topology, it's a compact space. Actually, it can be equipped with a metric to become a compact metric space. And this shift map is a homeomorphism of this, a self-homeomorphism. So you get what I usually call a topological system, some compact space with a self-homeomorphism. And this is what a shift of finite type is. Anything of this form. So this is called a SFT. And I'll point out that this is not the original definition of shift of finite type. Some people sometimes are puzzled by this. I mean, like historically, they were defined by taking essentially what I'll call the full shift, which I'll describe in a minute, and then forbidding some finite set of words from appearing and looking at what object you get by forbidding some finite set of words. That's the finiteness in the name shift of finite type. It turns out that this definition I gave here is equivalent to this notion of forbidding some finite set of words from appearing. And one of the things that was discovered, I mean, through many long years, is that this presentation is substantially better in some sense, or has a lot of advantages in terms of thinking in terms of graphs and walks. So today I'll think of SFTs just defined in terms of graphs. So one key thing is that SFTs are arguably the most important object probably in symbolic dynamics. Symbolic dynamics in general studies subshifts, which are just compact subsets of a shift of finite type that are closed under the shift map. They in general need not be SFTs. SFTs are kind of the most fundamental ones. But in general, subshifts can exhibit a wide, like really wild range of dynamical behavior. And the SFTs certainly play like a really key role. They kind of originally rose out of coding. So classically, people were very interested in studying the structure and the dynamics of like smooth systems, like Anosov diffeomorphisms, or say maybe hyperbolic toral automorphisms, or generalizations of this. And one of the main tools that was found was that you can choose certain partitions, Markov partitions, of these systems. And when you do this, you get a cover from an SFT. And it's a very good cover. And this coding, which gives you this cover, gives you a lot of dynamical data about the underlying smooth system. And SFTs kind of arose from this. One of the early questions was that if I have a system and I can code it two different ways, I can generate two SFTs. And the question is, when are they the same? Okay, you need to say what does the same mean. So this is essentially the classification problem. When are two shifts of finite type, I'll call it topologically isomorphic. In dynamics, typically one uses a different word. Sometimes it's more common to see topologically conjugate. I'll stick with topologically isomorphic for now. This problem is still very much open, by the way. So there has been a lot of results, a lot of progress, but the general problem is still essentially open. And just to be clear, what does it mean for two systems to be topologically isomorphic? It means you have a homeomorphism between their domains that intertwines their respective actions. So again, sometimes this is called topologically conjugate, but
sorry, when you say open, I mean, isn't this the kind of equivalence that is, I mean, that you can decompose it into outsplit and blah, 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 certain
yes, it's true.
So you mean there is no invariant that tells you on the nose whether
yes, exactly. It's a good question. What do I mean by like when are two SFTs topologically isomorphic? Yeah, to be more precise, either one, a complete list of invariants, which are kind of understandable, or two, an actual algorithm. So, for example, it's still not known whether it's decidable, whether there even exists or can exist an algorithm to determine. And yeah, I mean, I'm going to say a little bit more about things in terms of an equivalent version of outsplits, input splits, and amalgamations. And you're right. Yeah, I mean, there are ways to reformulate this, but for example, it's not known if it's decidable. So that would be a one version of this. So let me just quickly maybe show some examples just to be clear. If I take the graph with one vertex and two edges from this vertex to itself, the set of bi-infinite walks is usually called the full shift on two symbols. You could label the edges A and B. So points in X, gamma, A here are just bi-infinite strings of A's and B's. And this corresponds to the matrix 2, this is the adjacency matrix for this graph. A second example would be something a little bit larger. I could take the matrix B1210, form associated graph, which has this as its adjacency matrix, which looks like the one I'm drawn there. Here I have four edges. I could label them A, B, C, D, and then I take a bi-infinite walk on this graph. So here's a short exercise. If you get bored, you can show that these two shifts of finite type are not topologically isomorphic. Actually, I kind of gave away the answer, but
So sorry. What is the? I mean, the vertex out of which the edge D goes
yeah,
has only one edge going out of it.
yeah.
But yeah. Okay, so that's yeah. Okay.
Is okay?
Okay, yeah, sure.
Good. Yeah, you can prove that these are not isomorphic kind of for a pretty simple reason, which is that the first one has two fixed points for the shift map, and the second one for the shift map has only one fixed point. Actually, you can see that immediately from the graph. Fixed points correspond to self loops. And you should just check that if two SFTs are isomorphic, they must have an equal number of fixed points. In some sense, that's the most basic and weakest invariant you could think of for topological isomorphism would be to have the same number of fixed points. So Williams introduced this notion of strong shift equivalence, which a priori doesn't look like it has much to do with shifts of finite type, although you can maybe guess that there's some connection in terms of adjacency matrices for the directed graphs that present them. And indeed, this is the case. And what Williams proved, his motivation for this is the following theorem. So he showed two shifts of finite type defined by some graphs, gamma 1, gamma 2, are topologically isomorphic if and only if their respective adjacency matrices are strong shift equivalent over the non-negative integers. And I'll emphasize now that the Z plus is a really important part of this theorem in a way that's kind of the heart of some of the difficult questions that I'll mention later. Is passing between Z plus and Z. And at first, it looks really fantastic. I mean, it is a fantastic theorem. It's really a fundamental result. It kind of transfers the question of classification into this question about matrices. And at first, that seems more promising. So just to remind you, the adjacency matrix of a finite directed graph is defined as follows. So in the same paper, Williams also defined a second equivalence relation called shift equivalence. So again, if you take a ring or semi-ring R and you have a pair of square matrices A and B, you can define them to be shift equivalent over this ring or semi-ring. Again, if there exists a pair of matrices R and S, which need not be square. And now you introduce a lag, L. L is usually called a lag, such that the following four equations are satisfied. And when you first see this, it looks a little bit unpleasant, maybe. But if you imagine for a second, if L equals 1, then the first two equations are just the equations for elementary strong shift equivalence. And actually, the second two automatically hold if L equals 1 and you have the first two. But in general, you may have a larger lag, and then you need to ask for the second two as well. So this is, in fact, always an equivalence relation on square matrices over your semi-ring. And it's an easy exercise to show that the relation SSER always implies SER. I essentially gave away the reason. When L equals 1, the first two equations of SE are the same as strong shift equivalence. And then the exercise is just to check that when L equals 1, the second two equations hold automatically. So in general, it's always true for independent of the semi-ring that strong shift equivalence over R implies shift equivalence over R. So shift equivalence is a kind of a coarser relation. And the thing is that at first glance, it looks more complicated. I mean, you have four equations, you have this lag. And the funny thing that has kind of transpired over many years is that it's in fact kind of an easier relation to understand. It's a much more natural relation in some sense, even though the defining equations or the definition looks worse. It's actually much more manageable than strong shift equivalence. So this is an absolute typo here. Now that I'm reading it, this is clearly wrong. So the plus should be in the first part. So it should say clearly SEZ plus implies SEZ. If you're strong shift equivalent over the non-negative integers, you're certainly if you're shift equivalent over the non-negative integers, you're certainly shift equivalent over the integers. So yeah, careful, there's a typo. And if you take two square non-negative Z plus matrices, you could ask, okay, how much nicer is this relation SEZ or SEZ plus? And SEZ, so shift equivalence over Z, turns out to be really a nice relation. I mean, it's just algebraically quite natural. Very natural, I want to claim. So if I take two non-negative square matrices, what is shift equivalence over Z? Well, there's some immediate invariance. They have to have what you could say is the same spectrum away from zero. One way to write this is in the following form. Another way to say this is that they define equivalent zeta functions. So essentially their set of eigenvalues away, ignoring zeros, must be the same. And in fact, something even stronger is that you can say that A and B have the same Jordan form away from zero. So away from zero, I mean the following. You could take a matrix A, it's going to have possibly some kernel, but you can restrict it to the maximal subspace that it acts on which it acts non-singularly. And look at the Jordan form for that. And that's what I mean by the Jordan form away from zero. It's essentially the Jordan form where you delete any block corresponding to zero eigenvalues. So you ignore zero eigenvalues. And actually, containing that is an important idea that shift equivalence kind of ignores zero eigenvalues. It kind of looks stably with a matrix. And actually, you could maybe guess that because you start taking powers, you have this lag. So if something happens eventually, and you kind of kill off any kernel. And a nice fact is that if you take two invertible matrices over the integers, they'll be shift equivalent over Z if and only if they're actually conjugate, if they're similar over Z. So there the relation is a very natural one. In a sense, I think the perspective that we have now is that shift equivalence can kind of be thought of as stable similarity. And if I go back to the previous example, 2 and then the other matrix 1, 2, 1, 0 are not even shift equivalent over Z. So here you could use kind of a really heavy-handed machinery to prove that those shifts of finite type are not isomorphic because they're not in shift equivalent over Z. But are not shift equivalent over Z. Why is that? It's just a short exercise. If these two matrices A and B were shift equivalent over Z, well, they're both invertible over Z. So by the previous fact, they'd have to be conjugate over Z. And then you can just check using a small trick that cannot happen. So they're not shift equivalent over Z. So shift equivalence over Z also keeps track of some arithmetic information because you're not passing to the field Q. Okay. So Williams introduced this second relation with kind of aim at understanding strong shift equivalence. And he made actually, this is not the original history of this, actually kind of erroneously proved that shift equivalence over Z plus implies strong shift equivalence over Z plus. This proof, of course, had a mistake, and then it became a conjecture called Williams' conjecture. So I already mentioned that SSEZ plus always implies SEZ plus, and he conjectured that the reverse holds. And this problem was very heavily studied for many years. And there was a great deal of work, which I can't really like survey in a short time. So some key names are Kim, Rausch, Boyle, Krieger, Williams, of course, also. And eventually it was found that the conjecture was false. So they found some counterexamples. Actually, the first counterexamples were found by Kim and Rausch using a lot of machinery developed by some of these authors. So they produced in 1999 a pair of 7x7 matrices, which they proved they are shift equivalent over Z plus, but they're not strong shift equivalent over Z plus. And these matrices were not very easy to find. My understanding is that they had to use a computer. It took quite a while. And I want to emphasize that despite the existence of these counterexamples, there are not very many known counterexamples to the conjecture. And there's this pair found by Kim and Rausch, which was kind of with a lot of work. There was another pair found by Wagner, kind of using similar ideas. So they're somewhat similar pair of matrices, but different. And there are very few other actual known counterexamples. So this question, shift equivalence for strong shift equivalence, there's kind of two ingredients to it. If you're looking at the question in the context of Williams' conjecture, there's the order part, making sure to be non-negative, and then the algebra part over Z. And it turns out that the important case of the conjecture is what's called the primitive case. So a square non-negative matrix is called primitive if there's a power such that every entry is positive. In that case, eventually all the powers are positive. This has a dynamical interpretation for the associated shift of finite type. The SFT associated to such a matrix is what's called topologically mixing. And it's the most fundamental case in dynamics. So the conjecture, the primitive case, is kind of the core, most fundamental case. And it turns out that for primitive matrices, shift equivalence, the order and the algebra part are equivalent. So this is a very nice fact. If you have a pair of primitive non-negative matrices, then A and B being shift equivalent over Z plus is equivalent to A and B being shift equivalent over Z. And those are both equivalent to a third condition, which is that there is an isomorphism of some associated dimension groups, which intertwines the respective actions. So when I say the respective actions, delta A, for example, I mean that A will induce a canonical automorphism of its dimension group GA, which I'll call delta A. So what do I mean by dimension group? So here, I mean, you have this non-negative integer matrix A, and you can take the direct limit of this sort of stationary system, and you get an abelian group. This is a finite rank abelian group. And A will act or induce some self-automorphism, which I'll call delta A. And this pair is essentially a complete invariant for shift equivalence over Z, and in the primitive case, equivalently, shift equivalence over Z plus. So this is kind of part of what I mean when I say that shift equivalence is sort of well-behaved algebraically. So just working on the algebra side, you have a very natural question. Ignore the order part for a minute. Is it true that shift equivalence over Z implies strong shift equivalence over Z? So let's just work on the algebra side for a sec. And the answer is yes. Actually, this was known even to Williams, who gave an argument that was not entirely complete, kind of missing a step, but can be made to work. And then there was later a very nice proof given by Efros, which never appeared in print, And actually, more proofs have appeared since then. And what emerged out of this was something called the algebraic shift equivalence problem, which asks for which rings is it true that shift equivalence over the ring implies strong shift equivalence over the ring. And Boyle and Handelman took a look at Afros's argument and saw that it works actually just for PIDs as well, and it can be made to work. Okay, you need to do a little bit of extra stuff, but you can be made to work even over Dedekind domains. So they generalized this. So the answer is yes. SER does imply SSER for Dedekind domains, in particular for PIDs. And this kind of got situated into what's called a general Williams problem, which is that you want to know when SER implies SSER plus. Sorry, SER plus implies SSER plus. And the route you can try to take is in the primitive case, 1 on the left, usually use an equivalence. SER plus usually is equivalent to SER in the primitive case. And in 2 is the algebra question, which I'm going to discuss quite a bit. When does SER imply SSER? And 3 is usually the mysterious remaining part. So now we know quite a bit about 1. We know a lot about 2. And 3 in general, we still don't know much about. Even in the case of Z, as we saw. Okay, even just on the algebra side, studying the relation SSE over the entire ring, it's also motivated by several things. There are a lot of interesting questions about inverse problems for non-zero spectra. You take a subring in the reals and you ask, what can the non-zero spectrum of a non-negative matrix over this ring be? And what can the non-zero spectrum be for an irreducible or primitive matrix over the subring of the reals? And there are a lot of conjectures about this, so-called spectral conjectures, about conditions which tell you when a ring, when for a given subring, say, of the reals, a matrix can be SE or SSE over that ring to a primitive matrix. And this is known to be solved. So solved means they give the sort of optimal conditions over R and also over Z. But in general, this is still open for a general subring. And on the symbolic dynamic side, there are other rings that turn out to be very useful for studying symbolic systems. So the case of where your ring is the integral group ring of a finite group, this corresponds through this matrix framework to studying finite group extensions of shifts of finite type. So skew product.
Do you allow non-commutative groups there?
Yes. Yeah, it can be an arbitrary finite group. In which case your ring will not be commutative. So the non-commutative case is actually quite important, even in the symbolic set. And then there are several more. So another key case is like Laurent polynomials, which corresponds to sort of distinguished isomorphism of SFTs, preserving some Markov measures. And there are various matrix frameworks using other rings. So ZG are these things where you have this strong shift equivalence framework corresponds to topological isomorphism. So one of the things that emerged at some point, and then Boyle and I myself really kind of developed it further, is that there are really nice connections between algebraic shift equivalence notion and algebraic K theory. So I'm going to introduce a little bit of notation from K theory just to state some theorems. Before I do, let me just kind of mention kind of at an intuitive level, one might expect this because in a way, some low or like low level algebraic K theory, you're trying to do linear algebra over a ring. And then it's very natural to expect this because shift equivalence and strong shift equivalence is saying something about linear algebra over rings. So that there's a connection at all is not surprising. But what exactly it is, I'm going to describe in the next few minutes. So you take a ring R, you can take GLN R. This is the group of n by n invertible matrices over the ring. And you can stabilize it. So you include GLN into GLN plus 1 by just putting a diagonally in. And then you could take the direct limit, so take the union of all these, and you get stabilized general linear group, GLR. So this is a group, GLR. And you can do an analogous thing for elementary groups. So ELNR is the subgroup of GLNR generated by elementary matrices. So matrices which differ from the identity in at most one spot. So that generates a subgroup of GLNR. And you can likewise stabilize elementary matrices. You get the stabilized elementary group. So ELR is a subgroup of GLR. And in 1950, Whitehead proved an amazing theorem, kind of, one can argue, was kind of like the beginnings of some algebraic K theory. He showed that, in fact, the stabilized elementary group is algebraically distinguished and that it's the commutator of GLR. So if you want to compute the abelianization of GLR, well, it suffices to just mod out by the elementary matrices. This is quite useful because the abstract commutator, okay, it may not be clear what this is, but the elementary group is a very concrete subgroup. And once you have this, so historically, it preceded that they define this group K1 of R to be the abelianization of GLR. So in terms of Whitehead's theorem, K1 of a ring is just the general linear group of this ring mod out by the elementary matrices. So the abelianization of the stabilized general linear group over your ring. So it's an abelian group. It takes as input a ring, it spits out an abelian group. And I mean, you can play around with elements because, elements of this abelian group are equivalence classes, stable equivalence classes of invertible matrices. And the operation, you can either just take the direct, like literally multiply them once you make them the same size by adding ones if necessary, or taking the direct sum. Those produce the same class. So it's not so clear with the first operation that it's an abelian group, but it's very clear with the second operation that it's an abelian group. And this assignment is functorial. So this is a functor from rings to abelian groups. And there's just a little bit of structure worth pointing out, which is that when you have a commutative ring, you have the determinant map, of course. It takes you from GLR to the group of units of your ring. And this gives you a homomorphism from K1 to the group of units of your ring, because the determinant respects equivalence classes in K1 of R in the quotient. And SK1 of R, this is defined to be the kernel of the determinant map. So this is just classes of matrices in K1 of R, classes of invertible matrices, whose determinant is 1. And you get an exact sequence because, well, every unit in your ring can be made into a 1-by-1 matrix. And that's an element of K1 of R. So it's actually surjective. And just a little bit of general knowledge about K1. So if R is a field or even a Euclidean domain, it's a nice exercise to show that SK1 vanishes. This is basically just linear algebra because you can do row and column operations. That's essentially the idea here. And in that case, K1 of R is going to be isomorphic to R cross. So with units. More generally, if R is an integrally closed subring of a finite field extension of Q, then it's kind of a very famous theorem of Bas-Milner-Serre that SK1 vanishes. So this is a very deep and difficult theorem. And for group rings, which are kind of relevant actually even in the dynamic side, it turns out that K1 is very wild. I mean, SK1 of ZGs can be highly non-trivial, and the calculations are very complicated. So just as an explicit example, SK1 of the integral group ring of this particular finite group is non-trivial. So I need to define an auxiliary group, another group called nk1 of R, and you arrive at this as follows. You can take the polynomial ring over your ring and look at the evaluation map at 0. This is a homomorphism from polynomials into R, and you get an induced map on K1. So this is a very concrete thing. In fact, it just takes an invertible matrix over the polynomial ring and replaces all the t's with zeros, and you get an invertible matrix over R. The kernel of this is called nk1 of R. So this is an abelian group. It's an abelian subgroup of K1 of R of T. And one very useful and kind of fundamental fact about this group, it's sometimes called Higman's trick, shows that nk1 of R is just the classes in K1 of R of T, which can be written as I minus Tn, where n is a nilpotent matrix over R. So this is the first the first case showing that nk1 of R kind of, is associated with nilpotent matrices in some form. And if R is a field, a PID, or a Dedekind domain, then actually this group nk1 of R vanishes. In some sense, it vanishes for very nice rings. In fact, if R is even just a Noetherian regular ring, then it vanishes. But it doesn't always vanish. And a very clever argument of Farrell shows that if it doesn't vanish, then it's very big. So as an abelian group, it's not finally generated if it's not zero. And just as a concrete non-trivial example, it turns out that for some finite groups, for example, Z mod 4, nk1 of the associated group ring does not vanish, of the integral group ring does not vanish. And these calculations are in general quite hard to do. So, okay, it's maybe not so hard to show it doesn't vanish, although even that's not easy, but saying what this group is quite challenging. So as I mentioned before, I have a bit of a typo here again. It should be between nk1 of R. So the connection between nk1 of R and nilpotent matrices was spelled out by Higman's theorem. And in fact, it's really convenient and actually kind of important, especially on the K-theory side, to define an equivalent form of nk1 of R. So let me define another group for you. A very interesting group, actually. So you take your ring R and you define the group nil 0. You take the free abelian group on the set of generators, classes of nilpotent matrices over your ring, where the classes are determined by the following relations. So if two nilpotent matrices are similar over your ring, or conjugate over your ring, then it's the same class. And you have this relation defining the operation plus, which is you can put anything in the top right corner, and that is equivalent to adding the two. And then, of course, you want 0 to be 0. So this is a group. It's an abelian group by construction. I mean, it starts as a freely abelian group, and then you introduce some relations. So it turns out that this group is actually isomorphic to nk1 of R. This is part of some kind of fundamental theorems in algebraic K-theory. Actually, the isomorphism is very explicit. If you have a class in nil 0, so some nilpotent matrix over your ring, you descend it to the polynomial matrix I minus Tn. That's an element of nk1 of R, because if you set t equal to 0, it goes to the identity class, so it's in nk1 of R, and that map is an isomorphism. Okay, proving it's an isomorphism is not exactly trivial, but it needs some machinery. And this kind of fits in a broader setting. This group nil 0, it arises in K-theory as K0 of some category of nilpotent endomorphisms of projective R modules. So it's part of what I find to be a very useful philosophy that endomorphisms of finitely generated projective R modules kind of corresponds in kind of a canonical way to what are called monic torsion R of T modules, projective dimension less than or equal to 1. What does that mean? It means that you can kind of go between endomorphisms of finitely generated projective modules or special R of T modules. So I might say a little bit more about this later in a concrete way. So, but just as a kind of glimpse of this, shift equivalence is a relation on endomorphisms, and you could kind of go to the polynomial point of view. And one thing you can prove is that if you have a pair of square matrices A and B over R, they're shift equivalent over R if and only if their respective polynomial cokernels, the cokernel I minus TA, are isomorphic, as are T modules. And in fact, this is equivalent to finding a pair of invertible matrices, U and V over the polynomial ring, that takes I minus TA to I minus TB.
So, sorry, there when you write R of T module, right? You could as well write R of TT inverse modules.
Exactly, that's correct. Yeah, here when you take these cokernels, you sort of force T to be invertible. Or, I mean, yeah, you force T to be invertible or A to be invertible equivalently. And exactly, it's equivalent also to the RTT inverse modules being isomorphic as RTT inverse modules. Okay, so shift equivalence over R has a nice interpretation at the polynomial level. It's very algebraic. The natural question is, what is strong shift equivalence over a ring in terms of the associated polynomial matrix I minus TA? Does it have an analogous description? And the answer is yes. So one of the things that Boyle and I proved is that for square matrices over R, they are a strong shift equivalent over R if and only if there exists a pair of elementary matrices over the polynomial ring whose left and right action takes you from one to the other. So the thing is to compare this with the last statement of the previous theorem. Shift equivalence corresponding to finding invertible matrices, so U and V and GLR of T. Here strong shift equivalence corresponds to finding elementary matrices over the polynomial ring. The proof of this is kind of a long, but a mostly elementary thing. And I won't say too much about it. It's not maybe so interesting. But I do want to say that I find this theorem very interesting because it shows that strong shift equivalence as a relation on endomorphisms kind of arises very naturally from the K-theoretic point of view. I mean, you can look at GLR of T equivalence. From the K-theory point of view, it's natural to ask about ELR of T equivalence. And it shows that for matrices of the form I minus TA, this is exactly strong shift equivalence. So a natural question, once you have this, is the following. If I take a ring R, going back to this algebraic shift equivalence problem, how are the shift equivalence classes over R refined by the strong shift equivalence classes? So we know for Z, for example, they're equivalent. And to try to formalize this, if I have a square matrix A over my ring, I can let A SSE or A SE denote the strong shift equivalence or shift equivalence classes over the respectively over the ring. And there's a function. This just takes, it maps SSE of R, which is the set of strong shift equivalence classes of square matrices over R, to the shift equivalence classes, SE of R. And by the previous theorem, it's not so hard to prove that for a nilpotent matrix, your class is 0 and nil 0 if and only if that nilpotent matrix is strong shift equivalent over your ring to 0. Actually, it's more or less immediate by combining a lot of previous theorems. And the question now is essentially, what does pi look like? What are the fibers over a matrix or over a class in SE of R? Well, toward describing this, because of this previous theorem that nilpotent vanishes in nil 0 if and only if it's strong shift equivalent to 0, you get a well-defined action of nil 0 on the strong shift equivalence classes. If you have a nilpotent matrix N, it acts on the strong shift equivalence class by just direct summing with the nilpotent matrix. And the thing we proved is that if you pick any square matrix, you have a general ring, and you pick any square matrix, that the orbits of this action essentially give you the sizes of the fiber. Actually, I mean, the orbits of this action are in bijective correspondence with the fiber. In other words, there is a bijection between the set of strong shift equivalence classes of matrices which are shift equivalent to A and the orbit of the strong shift equivalence class under this action of nil zero. So it parameterizes the size of this refinement, this orbit under nil zero. In particular, you get immediately the following corollary. For any ring, if nk1 vanishes, well, then nil zero vanishes. And if nil zero vanishes, then by this theorem, it means that the fiber of the shift equivalence class is trivial. And so if nk1 vanishes, then A and B are strong shift equivalent over the ring, if null, if they're shift equivalent over the ring. And actually, the converse is true. So this gives a characterization of exactly for which rings strong shift equivalence and shift equivalence are the same. It's precisely characterized by this group nk1 of R. So in light of this theorem, it's kind of, a relevant question that is to try to understand the orbits of this nil zero action on strong shift equivalence classes. And this is where things get a little bit harder. So you can look at the stabilizers. If you pick a matrix A, you can just look at the classes in nil zero, the nilpotent matrices that don't change the strong shift equivalence class when you direct something. This is the stabilizer of that action. And what we proved is that in general, these stabilizers are non-trivial. If A is nilpotent or invertible, then the stabilizer vanishes, but in general, the stabilizers will not be trivial. And in fact, if you take the union of all the stabilizers, you actually get almost all of nil zero, something we call S nil zero, a set of classes of nilpotent matrices where that determinant is 1. So in general, you'll have non-trivial stabilizers. So if R is commutative and reduced, then S nil zero equals nil zero of R. In this case, everything in nil zero will appear in some stabilizer. And the proof of this theorem is significantly more difficult than the previous ones. So we had to use a lot of machinery from K-theory. We had to use a lot of things about K-theoretic structure of non-commutative localizations and some old work of Nanishev on presentations for K1 of exact categories. So there are a lot of ingredients into this last theorem. So in general, kind of winding up toward the end here, the structure of these stabilizers is very mysterious to us still. We don't really have a good answer. And just as a broad question, if you have a ring R, you can ask for some kind of satisfactory description of when the stabilizer is trivial. I mean, we have some conditions, but we don't have the complete answer. And we know that in general, this is a non-trivial problem because there are non-trivial stabilizers. So when is the stabilizer trivial, or what does the stabilizer look like? We don't know. And there's a more precise but much more technical conjecture in a paper of Boyle and myself where we prove these theorems. It's stated in terms of the kernel of some map on K1 between some non-commutative localization. So it's a little technical to state, but there's something very concrete there. And maybe I'll skip this slide actually for the sake of time, because I want to get to this table as one of the last things I'll show you. So this table kind of spells out a lot of summarizes a lot of what I've said. If you have an endomorphism of some free R module F, you can choose a matrix representation, choose a basis, and then you get these correspondences. So endomorphisms on the endomorphism side, similar to class, the matrix is same as the GLRT conjugacy class of T minus the matrix, which is the same as the isomorphism class of the RT module P. SSE of R is the same as the elementary ELRT equivalence class of 1 minus TA. And SER is the GLRT equivalence class of 1 minus TA. It's a little unclear what exactly the R of T module relation is for SSER. So this is another question. Exactly what is this interpretation? But this kind of summarizes a lot of what the perspective is now. So some final remarks and questions. If you go back to the classification, Wagner has a very nice survey paper where he outlines. So he produced some counterexamples of the conjecture as well, using invariance, taking values in K2 of the dual numbers, which is non-trivial. And these invariants, I mean, he defined them using K-theory. They turned out to be actually essentially the same as these other invariants that Kim Rauch had used, which were dynamically motivated. This is still not entirely well understood. So I think one of the interesting questions would be to try to sort of de-polynomial these invariants of Wagner. So we know that there's a sort of philosophy you can do things on the polynomial side or on the endomorphism side. One thing I don't know, and it would be interesting, is figuring out what Wagner's invariants mean just at the endomorphism level. So without passing to the polynomial side. And that's where I'll stop. Thank you.
Thank you very much. It was very enlightening talk. I wondered how do Niemann-Ranitsky non-commutative localization paper get used? I mean, they produce a long exact sequence relating the K-theory of the ring and the K-theory of the localized ring and some need term.
Yeah.
Where do you need to localize and how does this come up?
The idea is the following. If I go back to, it's in this theorem. The idea is that you want to pass from K1 of R of T. You want to localize GL of T. Or actually, in fact, I mean GL of T is already good. You want to localize over R of T. You want to make matrices of the form I minus TA invertible, basically. That's the one you want to localize.
Mm.
That's the funny thing about this setup, is that in a way, yeah. So let me answer your question first. Niemann and Raditsky, yeah, they study these cone localizations and these non-commutative localizations. And here the idea is that you want to pass from square, not necessarily invertible matrices. You want to force them to be invertible. And the reason that it seems kind of relevant is because strong shift equivalence on the polynomial side corresponds to elementary equivalence. And so you'd kind of want to work K theoretically. I mean, if everything was invertible, then the strong shift equivalence classes correspond to classes in K1 because you're just working up to elementary equivalence, and there K1 works fine. The problem is that I minus TA in general is not invertible over the ring. And so you could try to force it to be invertible, and you use this non-commutative localization.
I see.
Yeah. That's the funny thing I want to mention about this setup, is that if you just try to naively adapt K1's definition to non-invertible matrices, so you just take elementary equivalence over the polynomial ring, this is just, you arrive at strong shift equivalence on its own.
And what is this? You said in your paper you have another more precise conjecture involving some map at the K1 level.
Yeah.
Is it? I mean, if it's not elementary enough because it involves K theory tools, I mean, the audience is familiar with K theory, so.
Good. Yeah. I mean, I can say that I think the one version of the conjecture, I'm trying to think if this is the way we phrase it, but I think it's equivalent to the following, that in the non-commutative case, so in the commutative case, I mean, the part 2 of the theorem essentially shows the relationship between the stabilizers and nil zero. And the conjecture is about the general case, so non-commutative case. And there, the conjecture is that the union of all the stabilizers should coincide with the kernel of the map on K1 from R of T into a certain non-commutative localization of R of T. Namely, you localize at the set of reverse monic polynomials. So you could take the set of polynomials that are like reverse monic. So basically determinants of I minus TA, but you don't have determinant because it's non-commutative. So you localize those polynomials you get a map from K1 of RT into the K1 of this localized ring, and the conjecture is that the union of all the stabilizers should be this kernel.
Mhm. Mhm. Okay.
I mean, I think we know basically nothing about the non-commutative case in terms of this conjecture. Like we don't even have toy examples where we know the answer.
And another thing is, except for a brief passing remark about uh, shift equivalence over Q, all the examples uh, uh, contain Z, and you didn't invert anything. Right? So I wonder
Yes.
if rings that contain Q as coefficient rings make are not interesting for some reason.
They are interesting, actually. So I just failed to mention them.
Yeah, because I mean, for these nil groups, nil K groups, if you are over Q, then there is I mean, if you have a commutative algebra that is of finite type over some field that contains Q, then you can these Milky groups are isomorphic to certain variant of the Cauchy homology groups,
Uh-huh.
and so you kind of have a handle of how to compute them. Say. Uh,
Ah,
but I don't know if that would be useful
ah.
for anything.
That might be interesting because we have one example that we used in another application. So it turns out that the ring Q adjoin TT inverse Z squared Z cubed. Yeah, nil zero does not vanish for it. And at some point, I actually did some explicit calculations that were like kind of difficult to do to try to generate non-zero classes in there. It'd be nice if there's some machinery to compute or to be able to say a little bit more about what these groups are.
Yeah. Okay. So what? Say again what the ring was slowly.
It's the rationals, and you adjoin T and T inverse,
Yeah.
and then Z squared and Z cubed, where Z is just some other variable.
So the node over
Yes.
tensor with the learned polynomials.
Yeah.
Okay.
You,
Yeah.
you,
Yeah. Hmm.
you tensor with the Laurents just to get nil zero to not vanish. I mean, the original node, I think nil minus one doesn't vanish, and then you bump it up a dimension. So.
Uh-huh. Uh-huh. Uh, yeah. Okay. So let me see.
Yeah, I mean, this was kind of surprising to us because this embeds a subring of the reals, for example. And yeah.
Uh, okay. So let me in the chat. I put a reference for.
Oh, thank you. That's very nice.
I mean, it involves it's. I mean, it involves Cauchy homology, but also the singularization, which in your particular case is easy.
Ah, okay.
You just the singular. I mean, the normalization of that is already the singularization, which is Q of TT inverse Z.
Uh-huh. 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 Ah, okay, cool. Thanks. I'll take a look.
Um, yeah. So, okay. So, are there any more questions from the audience? I have a tendency to monopolize the speakers. Okay. So, otherwise, I'll stop the recording here.